In this video, let us try to understand and make sense of the equations and all the mathematical part we've dealt with in the previous video, and also I need to make a few clarifications here. So the first thing that I need to clear is that we tend to actually apply Ohm's law in almost every situation that we find, and that is slightly wrong, and I'll explain you why. So the problem with Ohm's law is that it can be applied to only purely resistive, or rather circuits that have some resistance in them, and the circuit that we are dealing with right now is a purely inductive circuit, which means, so we have this sort of a circuit, right? It has some AC source, and you have the inductor here. And so the problem here is that in such a source, in such a case, now what is the net resistance of the whole circuit? Well, the resistance of the wire is negligible, the resistance of the inductor we've assumed is negligible, and so the resistance of the whole circuit is negligible, or rather zero. So if we try to apply Ohm's law, what we get is V equals, so we know that Ohm's law is V equals IR, and so we know that R in this case is 0. So okay, and so if I try to figure out I in this case, I can get I by shifting the R on that side, and what I get is I would be equal to, now what is the voltage? So firstly let me figure out what is the net voltage here. Net voltage, right? Now the net voltage is, so we know that the source voltage is something, let's call that V, and we've seen that in the previous video by Kirchhoff's law that the back EMF due to this coil here is actually equal to the source voltage. So the source voltage is exactly cancelled by the back EMF of this coil. So the net voltage is actually 0 in such a circuit, and the resistance is also 0. We just saw that the resistance is 0, and the problem with this is we get 0 upon 0, which is actually undefined. It could be anything, and so this simply tells us that Ohm's law cannot be applied to such a situation because it is not a resistive circuit, it is an inductive circuit. We cannot apply Ohm's law. So this is a wrong approach, and you need to stop using this approach. And yeah, and so just to clear this up, one more clarification that I need to add in here is that in one of the previous I think videos or somewhere you have been told that, so let us just take a simpler case of an inductor very bad drawing there, of an inductor connected to a, let's say, a DC source or simple battery. Now what you've been explaining that is that the back EMF is actually slightly less than the source voltage, and so you get a small amount of EMF, net EMF, or the net voltage in the circuit, and that causes some current, and the back EMF keeps on dropping, and you get more and more net EMF, and so the net current also increases. Now the problem with that explanation is that even a small, very tiny amount of net current in the whole, net voltage in the whole circuit would lead to a very, very high current, because there is no resistance in the whole circuit, right? This is a purely inductive circuit, there is no resistance, so that would cause a short circuit, and it would simply blast. I mean, it would simply overheat, and everything would just burn, right? So that is not a good explanation of it. What actually happens is that the current keeps on slowly increasing. Now now why does it increase slowly? Because if it increases, because the inductor actually avoids or tries to inhibit a rapid change in current, because a rapid change in current would mean a very high rate of change of current, which in turn would mean a very high rate of change of flux through the coil, and that would generate a very high back EMF. So to keep the back EMF equal to the source voltage, this the current, or the rate of change of current through the whole circuit, has to be not too high, and it has to be at a decent level, so that the back EMF generated due to that rate of change of current is equal to the source voltage. Now the source voltage and the back EMF would remain constant, equal to each other, and the rate of change due to that, because the back EMF is constant, we know that the rate of change of flux through the whole coil should be constant, and so the rate of change of current through the circuit should be even constant. I hope it's not getting too complicated. And so what, due to all this, what actually really happens is the current keeps on slowly increasing, and well, yeah, it increases to a certain point, and after that the circuit, because no circuit in real life has zero resistance, you would obviously get some heating effect, and the current would increase to that level, before which it's after which the circuit starts burning, and yeah, that's it. Now in case of an AC source, a similar thing happens, and let us look at that in a bit more detail. Now the next clarification that we need to make here is that we also connect, due to Ohm's law, we tried to connect this connection. Current is always proportional to voltage. Now that is true for resistive circuits, where the more voltage you have, the more current you get, but that is not true for purely inductive circuit. What instead happens is, well, I'll come to that in a moment. Now this can be related to another phenomena in physics, which is the relation between velocity and force. We tend to think that velocity, I'll represent that with V for now, is proportional to force, right? We tend to think that, so a higher force would lead to a higher velocity, right? That seems logical, but that is unfortunately not true. This is a wrong way of thinking. Now what actually really happens is, well, I'll come to that now. So we know that force is nothing but the rate of change of momentum, dp by dt. And what is momentum? Well, momentum is nothing but mass times velocity by dt, and I can, because mass of an object would remain generally constant, I can write that as force equals mass times dv by dt. Now removing the intermediate steps there, and let's focus on this. Now this tells me, so m is a constant, ignore that, but this tells me that the force is, or rather the rate of change of velocity is proportional to force. So if a higher force doesn't mean a higher velocity, it means a higher rate of change of velocity. I hope you can understand the difference. If I apply a very large amount of force, the velocity of that object would change very fast, right? And yeah, why we may connect a high velocity to a high force is that because of that high rate of change of velocity, after a certain amount of time you may get a very high velocity, but it may not be always true, right? So force is proportional, or rather rate of change of velocity is what is proportional to force, not velocity itself. Similarly, in the case of current and voltage in a purely inductive circuit, we've seen that in the previous video we had the equation rate of change of current di by dt, or rather I should put it this way, the source voltage V, sorry for the shaking camera, yeah, the source voltage V equals the back EMF, which is given by inductance, times rate of change of current. Now if you look at the two equations, they seem very similar. Well, that is so because they are pretty analogous, and that this forms a rather beautiful analogy. What you can draw from this analogy is that the voltage in a circuit, in a purely inductive AC circuit, is similar to the force being applied. So now to represent this, I would take the example of a pendulum here. So let's take the example of a pendulum being pulled to this position, and then it's left so that it moves like that, right? And so the voltage in such a circuit, a purely inductive AC circuit, is analogous to the force in a pendulum that is oscillating just like that, and the current in such a circuit is analogous to the velocity of the pendulum, right? Now let us understand this in a bit more detail. the more voltage you have, the more rate of change of current you would get in an AC circuit. Similarly, that is very similar to the case of to this case, where the more force of gravity you have, so obviously you have some gravity pulling it in this direction, and you can obviously resolve that along this direction and along this direction, and so I'll not get into that, but the point is you get some force due to gravity in this direction, and the more force you have in that direction, the faster this ball would, or the pendulum would, accelerate in that direction, right? The faster its rate, the faster its velocity would change in that direction. Yeah, so that makes sense. Yeah, and again you have this constant here, which is the mass of the pendulum, and that is very analogous to the inductance of the inductor in this circuit. Now, what is the role of the mass in this case? Well, mass is something that tries to avoid change. If it is harder to increase the velocity of a heavier ball, right? If something is more massive, has more mass, you need to apply a larger force to change its velocity by some given change, by some given change, yeah. And similarly, if you have an inductor with a large inductance, you need a higher voltage to get this get any desired rate of change of current, right? So inductance is something that tells you how much an inductor avoids change in current, so to speak, and mass of a ball or the pendulum is some value that tells us how much this object avoids change in velocity, or rather change in momentum. And yeah, so that is how you can connect the two. Now, another interesting phenomenon that you can see in this, and in this also you can relate, that is that, so we have let's consider three important positions: this extreme position, then let's consider this position, the mean position, and the other extreme position. Now, where is the force maximum on the ball? Well, here obviously the force of gravity is being cancelled by the tension in the string, so net force is 0 in this case. Here you have some force, some restoring force here, pulling the pendulum in that direction, and obviously when it reaches here, you have some restoring force in this direction, pulling it towards the mean position. So at these two extreme positions, you have the force being maximum. So here F is max, I'll just write an F there, F is max, here F is max, right? And velocity is 0. Velocity here is 0, right? It momentarily stops for a moment and then turns back and moves. Even here it momentarily stops, turns back and moves. And so you have Fm, F max, and velocity 0. At this position you have the maximum velocity, so it's moving the fastest here. You can obviously observe that when the pendulum comes, it moves fastest at the mean position. So it's V is max here, Vm, but the force we just saw is being the force of gravity is being cancelled by the tension in the string, and so the force in this particular case is 0. And now you can see very clearly that what we were assuming, you know, that misconception of force and velocity being proportional, that is not really true. When force is maximum, velocity is minimum. When force is minimum, velocity is maximum. So you see, it might happen this way, but yeah, what we can say is that the higher the force, the higher the rate of change of velocity. So at this point, the rate of change of velocity is maximum. At this point, the rate of change of velocity is minimum, and in this point, the rate of change of velocity is again maximum because the force is maximum. But you can see that the velocity is 0 where the force is maximum, and the force is 0 where the velocity is maximum. So now if we draw the similar analogy in this particular case, here what happens, and I'll draw a graph here to support my argument. So I'll just write the equation for this thing, the current through this thing. And if you remember, the current through a purely inductive circuit, so sorry for the video being a bit long, but yeah, the current in this circuit at any instant is equal to the maximum current times sine So this maximum current is nothing but V upon omega L, okay, Vm upon omega L, and I am sin omega t minus pi by 2, and yeah, and the voltage of the source voltage would obviously be Vm sin omega t, that is simple normal AC voltage. And if I try to plot these two, I hope I have some space here. I'll remove this thing to create some space. If I try to plot, let me first of all plot the voltage. So let's just take some voltage. Let's start at the maximum voltage here, and obviously it will follow the shape of a sine curve, just like that. That's my best attempt at drawing a sine curve. And so this is your maximum voltage. It will reach zero, negative voltage, zero, all that, and that is this. Now if I try to plot the current here, or let me use the this equation here, the voltage or the source voltage equals L times di by dt. And the important part to notice here is that rate of change of current is velocity. Sorry, is voltage. Very sorry. Voltage is the rate of change of current, right? And so if I begin to plot that here, so I'll just start at 0 here for current, because we are used to starting current at the mean value or 0 value. So we start here. The rate of change of current should be equal to the value of voltage. So here voltage is maximum, which means the rate of change of current should be maximum. So current at this point begins to increase very rapidly. So current starts to increase very rapidly, and it starts to increase just like that. And so you can see that in this graph here, the value of voltage keeps on reducing and reaches 0. So at this point the value of voltage reaches 0, and it gradually comes to 0, which means the rate of change of current should also gradually come to 0 by this point. So the rate of change of current, or at the slope of current, the current graph slowly reduces. See, the slope is reducing, and by this by the time it reaches this point, the slope becomes 0, or rather the curve becomes flat. So that is my best attempt at trying to represent this in this manner. So the first curve was voltage. Now the second curve is current. Here it reaches this flat part where the rate of change of current is 0. Now we can see that the rate of change of current, so the value of voltage is getting negative, so the rate of change of current should get negative, which means it should reduce. The slope should get negative, it should point downwards, as if the current begins to drop now, and it drops. At this point the voltage is maximum, has a maximum negative value, which means as it reaches this point, its rate of change of current, or the slope of this current graph, should be maximum. And see, it's maximum here, it's the steepest here, and then again its negative value begins to reduce to 0. So now the curve begins to gradually flatten out, and by the time it reaches here, it gets flatter and almost flat here. The rate of change of current becomes 0 at this point, and this trend continues further ahead. At this point, its rate of change of current is maximum, and then it reaches a max there, and yeah, you get this kind of a graph here. Now just to label it, this is the V graph, the graph of the voltage, and this is the I graph. I should have used a different color, very sorry there, but yeah. Now if we begin to analyze this, so you can see here we have two sine graphs. The only difference is one graph is actually shifted in one direction by 1/4 cycle. Now you need to look at this carefully, and if you try to think which of the two is moving ahead of the other? Well, see, the voltage graph reaches a peak at this point, and the current graph has to reaches the peak after this gap and this gap. So this is one complete wave, so this is a half wave, and this is 1/4 wave. So you can see here voltage reaches a maximum and here current reaches a maximum peak, but current reaches its peak 1/4 wave later, right? You have to travel forward in time for to see current reach its maximum peak. So current is reaching the maximum peak later than, so voltage reaches the maximum peak 1/4 cycle before current reaches its maximum peak. And what is 1/4 cycle? Well, that is represented by this pi by 2, and you will learn this in more detail when you study phases and all that. But yeah, that is the basic idea behind it. And the basic idea here is that the voltage is actually or rather the current actually lags behind voltage by 1/4 cycle, and that is clear here, by 1/4 wave or 1/4 cycle. And yeah, and what is actually going on here is that initially when you have a very high source voltage, the current begins to increase quickly because you have a very high voltage, and you know from this equation we know that voltage is the rate of change of current. So a high voltage means a very high rate of change of current, so current increases rapidly in this section here. And so here the battery is driving the current through the circuit, but this back EMF of this inductor, it's actually trying to, you know, slow down the rate of change of current. So that is why the current doesn't increase very rapidly. It increases at a decent rate, at a very high, at a pretty decent rate, not too high, not too low, and it keeps on increasing, and it increases till that point, till the point the source voltage is positive. As soon as it reaches 0, it stops increasing, and then it starts to decrease because the source voltage is now 0. The source voltage is no longer supporting it. Instead, as the source voltage gets negative, the source voltage is actually trying to oppose the flow of current. It is trying to switch the direction of current, but because, you know, this inductor is not very interested in change, it tries to avoid this change, and now the back EMF of this inductor drives the current, and this back EMF keeps on so this back EMF actually allows the current to move in the same direction for some time, and it falls slowly, and after, you know, some time, the current switches its polarity, switches its direction, and then begins to flow in the other direction. And so this cycle continues. And yeah, so what happens really is, for some time, for half the time, the battery is driving the current, and for the remaining half time, the inductor is driving the current. So what is happening in this section here? In this section, the battery is driving the current. It's the battery voltage that is actually responsible for the current. And during this section, so here obviously, if there was no inductor, the current would have increased quickly, but because there is some inductor, there is an inductor there, the current increases slowly. And so during this period, the inductor actually gets charged up. It is storing the energy from charge, the energy from this battery, from the source, in form of magnetic potential energy. So in this section here, it is getting charged up, so the inductor actually stores energy. I hope you can see that. Oh, it's not visible. Actually, I'm talking about this section here. In this section, it is getting charged, so it is storing. I'll just write a store there. It stores, and here in this small section, the battery is what is driving the current. And now in the second section, this section here, or rather, I think till here, in the next 1/4 cycle, it is the inductor that is driving the current. And in this section, the inductor is actually losing energy. So in the first 1/4 cycle, it is actually gaining energy and trying to store energy in the inductor in the form of magnetic potential energy, and the battery is the source is what is driving the current. and in the next 1/4 cycle the inductor is losing energy, and it is the inductor that is driving the current, because and the battery voltage is actually opposing the current. And this, you know, this tussle between the back EMF and the source voltage continues. So half the 1/4 cycle this powers the current and this opposes the current. In the next 1/4 cycle this powers the current and that opposes the current, and this continues and continues, and that is why you get a lag. And yeah, I hope the video is not too long, sorry for that, but yeah, that's it for this video.